Now let's grow our first causal forest. You are asked to fill in the gaps in the formula below. So, as you can see, we put seed so that no matter how many times we run it, it will always give us the same result. We say grow a causal forest, which is a function, takes different parameters in it, and then we save this into the cforest object. So what does causal forest function do? So X is the numerical matrix of controls, and we already created it before. Oops. Now the next thing, what is our Y? We saved it as Y object. What is our W, the treatment variable? We saved it as W. Number of trees. What do I ask? I ask 4,000 causal trees. So I'll put it 4,000 in here. Let's see whether I use that. Yep. So in the hint. Clusters. No, we don't have clusters. We don't need to specify clusters here. Sample fraction. To ask about sample fraction, 50%. We want to always sample only 50% of our data to grow trees. Remember, it has the machinery of random forest. It always bootstraps the data. So 50%, 0.5. Try. Yes, use all of the variables as potential split candidates by putting the correct and try. So we want to run actually bagging model. Well, actually we have just 6 variables, right? So what do we do? Number of columns of X. Now, minimum node size. Minimum node size. Require the node size to be 10 or more observations. Yes, we don't want to have too few observations in every single node. Honesty true, honesty fraction. Keep 50% of the sample data as estimation sample and 50% as training sample. So 0.5 it is. Honesty prune leaves true. Yep, we will prune the trees and tune. No, do not tune parameters. So 4. But you can actually, if you want, if you're curious and you're running it on your own computer, you can put all. Let's run the code. And I, in the end, ask, what is the cforest object? And it says, it's a GRF forest object of type causal forest. It has 4,000 trees. It has number of training samples, 1,000. It is basically the number of observations, right? Variable importance. And then it gives you variable importance. What it tells us is that the first variable seems to be very important. 77% of weighted average splits are done on the first variable, which, if my memory is correct, let's do like this. Names, data set. So the first thing is number of priors. Yes, so number of priors is the most important, then the rest is like, yeah. Now, variable importance, plotting trees. So here we have, remember, causal forest grows 4,000 causal trees on 4,000 different bootstrapped samples. And here, in this way, we can ask to plot the very first causal tree. See, I say index 1. Then we change the code below to access the 42nd causal tree. So you put here 42, run, oops, you see number of priors. It's the first thing that you split upon, then again a number of priors, and so on and so forth, and then you have this differently sized final nodes. Again, our causal forest splits how? Splits in a way that maximizes heterogeneity in treatment effects. Okay, so we can also do 15th and so on. So they all kind of look differently. See, as we bootstrap our data, we get different causal trees. And then we aggregate all those different causal trees, information from all of these causal trees, into one generalized random forest estimator. Find which variables are the most important ones for predicting heterogeneity of treatment effects. now we are again returning back how to get, remember the variable importance, and we see cForest. So this is, remember cForest is our object, and then we run this code and it says, okay, the first one is 77% of splits is done on the first variable. And let's do the quiz too. Yes, the first predictor is the most important, number of priors. Continue. Okay, here you're asked to show the average treatment effect. So first of all, this is the formula that gets you the average treatment effect based on the causal forest that you've grown. And you said target sample all, it means all, meaning that it finds average treatment effect. And the average treatment effect is 0.07. What? You need to answer this quiz to know what it is. Okay, so now you're asked to change the target sample to treated to get the ATT. So average treatment effect on treated, we say target sample. Now, please reweight the treatment effect by taking into consideration only treated observations, treated ex-offenders. And the average treatment effect on the treated is 7.3. Now let's return back to all, so overall average treatment effect. What does an AT here mean? And we need to think about it. And I hope you found out that it means 71 USD because our outcome variable is in thousands of dollars. This means that average treatment effect is in dollars. And since it's in thousands of dollars, it means that the effect of the job assistance program increased on average the income of the this should be the treated, but the expected average treatment effect is 71 USD, and then on the treated it would be $74. But anyways, this is the correct answer. It should be USD. Then the average treatment effect is very close to average treatment effect on the treated. Why is it so? You can answer it. Okay, here you are asked to run an OLS. Does the estimate of the average treatment effect using OLS coincide with the earlier estimate by the causal forest? Remember, we have the completely random assignment to treatment. It means that our OLS, if we just regress, so we take linear model and we just regress our wage variable on a job help variable, data equals data set. That's the summary of this. I'm not sure whether I put room here. Well, okay, let's do tidy. I like tidy. Yep. It says the average treatment effect is 6.6. So basically $66, not $71. So I think it's broadly in line with the average treatment effect. Yeah, it's not much lower, it's not much higher. Now we are asked to test whether there is heterogeneity of treatment effects, in treatment effects. So we use test calibration, about which I talked in the video lecture. So we do test calibration, and we supply the causal forest that we trained, and it provides us with estimates. It has estimate 1 in front of mean forest prediction and estimate of around 1 for differential forest prediction. And if you remember from the video lecture, it means that our causal forest actually performs better than just a constant treatment effect, because our estimate for the differential forest prediction is completely different than zero. So we can reject the null hypothesis that our forest prediction does not capture any differential prediction in treatment effects. So this is incorrect. The causal forest performs better than just a constant treatment effect model. It captures some heterogeneity in treatment effects. Yes, That's true. We can reject the null of no heterogeneity. That's also true, because we can reject the null of no heterogeneity. The mean forest prediction is correct. That's true, because if it was anything other than 1, it means our mean forest prediction is incorrect. But here, it's 1, so it's correct. So, submit answer. Yes. Exercise. Calculate average treatment effect for black and white ex-offenders separately. So, before, we remember when we put target sample O, without anything like this, it would have given you just the average treatment effect. Now we want to see how it is different. What is the average treatment effect conditional on the person being white? So we say ethnicity Caucasian is equal to 1. And we see that it's a bit lower. It's $55 instead of 71. So what is happening here? We put into the average treatment effect function, and we say use only subset, so target sample all, but we use only a subset based on the characteristics. And the characteristics are, so let's see so every time you see some code, what you usually expect you to do is to write it like, okay, what is X ethnicity Caucasian? Aha, it's numerical vector. So what would happen if we just put nothing in here and like first 6 rows and first 6 columns? Yeah, it's just our X matrix, right? And instead, if we put ethnicity Caucasian, it selects the column of ethnicity Caucasian. So this is the first 6 rows of this column in this matrix. So when we don't put this and we make equal 1, it creates logical vector, true or false. Some are false, meaning that ethnicity is not Caucasian, false, false, false. And this person, for example, first true, the observation number 12 is a person with Caucasian ethnicity. Okay, so that's the thing. We can also change it for something else. Change the code below to calculate average treatment effect for black ex-offenders. So how do we do this? It's simple. We just put 0. Ethnicity Caucasian is equal to 0. Remember, we have just white and black ex-offenders in this data set. And we see that for them, it's actually the average treatment effect is higher. It's $82. Now we can also do something else. Let's see. What other variables can we use? For example, female. Let's see what is the average treatment effect for women. Female equal 1. The average treatment effect is very low for women. It's just $30. And for men, it should be super high. Yeah, $80. Well, but it doesn't mean that it actually causes, right? It could be also coming from the fact that the number of priors among women is much lower than among men.